Chief Executive, distinguished guests, ladies and gentlemen, it's a very great pleasure to be here in Hong Kong for this very special event, the Innovation Summit, and of course celebrating the 200th anniversary of the Institution of Civil Engineers. I'm going to speak for a short while on the subject of innovation for smart infrastructure and construction. But firstly, I want to say that Hong Kong has a very special place for me. It's somewhere that I worked here as a young engineer in the 1970s, early 1970s, and I thought it would just be interesting for you. It's certainly interesting for me to see the difference in Hong Kong between the time when I was here as a young engineer and today. It's just one of the most impressive places in the world for the volume of innovative construction being undertaken. So I'm going to say a little bit about smart infrastructure. We've heard already quite a lot the word smart, and in the context of infrastructure, I think the best way of describing it is where it's the interaction between the physical world of infrastructure, whether it be transport, energy, water, any kind of physical infrastructure, interacting with digital in the form of sensors, Internet of Things, big data, machine learning, and where we see the two interacting is where we have smart infrastructure. And we have a lot of challenges facing our infrastructure. We have, in many cases, we have age as a problem. We have changes in loading, changes of use. We have uncertain future in terms of climate change and other factors. And these all have implications for us in terms of risk and resilience, in terms of the management of our assets, and of course they have implications for design. And we mustn't, of course, forget that some of our infrastructure is actually more vulnerable than we would like to admit. On the top left, you'll see a very dramatic collapse of a bridge in Minnesota, in the USA, without any warning whatsoever, leading to a very serious loss of life and about 100 cars going into the river. On the top right, you will see the very tragic collapse of a station in Singapore during construction, and on the bottom left, a bridge collapse in the UK, which was put a town completely out of action for a very, very significant period. And on the bottom right, burst water pipes is really becoming quite a problem in many parts of the world as our infrastructure ages. So the vision about smart infrastructure is expressed very well here in this diagram produced in The Economist magazine not very long ago. The Economist did a special supplement on smart infrastructure. They came to my university at Cambridge and spoke to us about what we were doing there and produced a special supplement. And this diagram encapsulates everything about smart infrastructure. It shows bridges, it shows a bridge, it shows buildings, it shows a tunnel, all equipped with sensors using wireless technology to tell us about how our infrastructure is actually performing. And they said in that article, and it's quoted on the slide here, that if a car can be made smart enough to spot when the oil is low or a brake light has failed, why not do the same for bridges, tunnels, and buildings? And that is absolutely the right question to ask. And the point is that there have been so many recent developments in sensor technologies that these provide major new opportunities for ensuring resilient infrastructure, for ensuring that we have smart infrastructure. My centre at Cambridge, the Centre for Smart Infrastructure and Construction, CSIC, is a government-funded initiative, but it's funded by both government and by industry, and its aim, its mission, is to transform the future of infrastructure through smarter information. It's smarter information that what this is all about. It enables us to make step changes in our construction practice. It enables us to establish a world-leading sensing industry. And it enables us, most importantly, to extend asset life and to reduce a lot of the management costs. This was a funding so far of around £22 million over a 10-year period, involving many organizations. We have about 50 industry partners. The top row you'll see are the infrastructure clients and operators, many of them government organizations. And the middle row are the consultants and contractors, very well known to many of you here. And the bottom row are the technology and information supply chain. These are the companies actually producing the software and the hardware that we use now for these advanced technology, advanced sensor technologies. There are 4 scales of challenge, really. We are dealing with sensors and data collection as the fundamental part of all of this, and then we have to analyze and interpret all that data, and we then convert that into information for our assets, and then we actually have a whole system for our cities and for our whole infrastructure systems. And so there is a relationship between all of these 4 blocks: the sensors and the networks, the data analysis and interpretation, the asset management, and the cities and infrastructure systems. So what is fundamental behind our sensors activity are field demonstrations. So we have now implemented new sensor technologies on around 100 different sites. I'm going to share just a few of these with you. Firstly, I'm going to say a little bit about innovative fiber optic sensing. So fiber optics are a fantastic new development for measuring strain in civil engineering infrastructure. So if we actually shine a laser down through a fiber optic, and we actually get signals transmitted through the fiber optic. 98% of the laser goes through the fiber optic. A very small percentage is backscattered. And if we plot the power against the frequency, we can find that if we have a strained part of the fiber, that strained part can be identified very precisely. So we can have hundreds of meters, even kilometers of fiber optic, and if one part of it strains, we can detect with extreme accuracy exactly where that strain is taking place and the magnitude of the strain. So in effect, the fiber optic becomes one long, continuous strain gauge. This has enormous power for infrastructure because fiber optic is very cheap. Crossrail, many of you will have heard about, is Europe's largest infrastructure project involving 21 kilometers of new subsurface tunnels right under London with 8 new subsurface stations. And we have implemented the fiber optics I'm describing in Crossrail, and here is just one example where some very large shafts have been built using diaphragm walls, a technique very well known to you here in Hong Kong. But the fiber optic is so easy to fix to reinforcement. So the reinforcement cages going down into the diaphragm walls, as you'll see on the right-hand side of the slide, have fiber optic fixed in the cages. The red ones are on both sides of the cage to measure bending, and the green ones are measuring hoop thrust in the shaft. So we now have a completely new understanding of exactly how these shafts perform, and most importantly, as to what extent they are over-designed. So what we can actually do now with performance measurements like this is to actually prove that we don't need to spend so much money on our infrastructure design. We can actually have the evidence to reduce what we do. The same has been done with sprayed concrete linings used for the tunnelling on Crossrail. This is a photograph of 2 of our Cambridge team fixing fibre optics into a sprayed concrete 11-metre diameter tunnel before openings were made on either side of the tunnel for passageways to measure exactly what happens when you make openings in tunnels. And so what this demonstrated was that the original thickening of the sprayed concrete to allow for the openings, this is a plan view looking down on the big tunnel with the two openings at the top and bottom you'll see, and the actual thickening was the red zone, but the additional stressed area was the blue zone. So actually there was quite a lot of additional concrete that was in fact proved to be unnecessary. And this is really important for the future, that we can use this kind of smart sensing technology to demonstrate that we can get away next time with less material, less excavation, less time, and safer construction. And we can also use fibre optic to retrofit into existing infrastructure. So here is a London Underground tunnel that was causing some concern. There was some movement going on of the linings, and you can see in the slide here fibre optic actually being installed to measure very precisely exactly what is going on. And that gave reassurance to the owner, London Underground, that all was in fact well, despite the movement going on. The fibre optic was able to provide the evidence that the tunnel was indeed safe and did not require expensive remedial action. And the last thing to show you is the power of wireless sensor networks and MEMS devices. Now by MEMS we mean micro-electrical mechanical systems. We can design tiny little sensors now that can be installed inside, for example, tunnels, but it could be bridges, it could be buildings, and these are designed to wake up at certain intervals, take a reading, it may be a reading of movement, displacement, or crack width, transmit to the next sensor all the way through to a gateway, through onto the internet, and inform the owners of the infrastructure exactly how it's performing. And this has been used again in London Underground in one of their tunnels, causing some problems. And so these there is the gateway shown there, and there are these other devices, all installed with no wires, very small, unobtrusive, and very cheap. And they can then be programmed to give the information needed to the owner of the tunnel. All of this relies on some very smart new electronics technology, and here you see a variety of different gauges. All of these are very small. So the bottom right-hand corner shows what looks like two tuning forks. These are actually etched into silicon chips. And so the size of that bottom right-hand figure is about 1 millimeter by 1 millimeter. Really, really tiny, barely visible to the naked eye. And this means that we can produce these kind of sensors now for civil engineering infrastructure applications extremely cheaply. And we have a team of very bright young students and researchers, and one of them is shown here, Heba Bevan, and she came from the organization ARM, A-R-M, a very successful spin-out company in Cambridge that specializes in microprocessors. And so the device is being held in her hand is called an Utterberry. It's already won a lot of awards, and it's very powerful. It has about the computing power of about 10 iPhones, all packed into that small little device that can be fixed wirelessly. It needs no wires, and it's been used extensively in Crossrail to measure temporary works behavior, but also left in place for permanent works measurement. So this is a really very powerful new technology. So there are a lot of examples that our group has been involved with. This is just to give you a flavor of the sorts of things that these new technologies can now provide us. We can look at pile tests, integrity testing. We can look at how high-rise buildings behave as they're being built. We can monitor performance in all sorts of ways during construction and over the entire lifetime of the infrastructure. And this is now a very powerful new way of improving the way we build our infrastructure and the way we manage our infrastructure. The ICE has produced best practice and technology guides on a number of the things that I've been describing to you, and these are very widely being referred to, and they're being adopted by industry on an increasing scale. And we have 4 of these volumes already produced. More will be coming in the near future. And there is a new proceedings journal, a new ICE proceedings journal, and the journal is called Smart Infrastructure and Construction. And I commend it to you. It has some really very, very innovative and important papers, and industry is adopting a lot of the kind of technology I've been describing to you. So in conclusion, simply to say that sensors, the digital world, data analytics are really now enabling us to build smart infrastructure. And that can really deliver value when exploited for managing our assets throughout the life of the asset, whether it be a road, whether it be a tunnel, whether it be a bridge or a sewer, a flood defense or a building. It enables us to have a full understanding for the first time of the performance of our assets. Think about that Economist article about the cars. We now can do the same for our assets during construction, throughout design life. It gives us the opportunity for greater efficiencies in design and performance. It gives us rational strategies for whole life maintenance and asset management. And it gives huge potential for transforming infrastructure, both old and new. So ladies and gentlemen, I hope that sets the scene for what I hope will be a very interesting conference today. Thank you very much.